Welcome to Securing Apps in the Open by Default Cloud with Winston House and Michael Wozniak. Just a few announcements before we begin. Please stop by the business hall located in Mandalay Bay on this level. And the Black Hat Arsenal is in the business hall level 2, this level as well. We appreciate if you can silence your cell phones. And please give a warm welcome to our speakers today. Again, Winston House and Michael Wozniak. Thank you.
Thanks. Cool. Take us away.
All right. Yeah, thanks for coming. I'm Michael Wozniak with the infrastructure security team at Snapchat.
And I'm Winston Howes on the application security team at Snapchat.
Yeah, welcome to the cloud. Here at Snapchat, we're primarily or almost entirely on cloud services. For us, this means AWS, GCP. There are others, and most of what we're talking about is could be used on those other clouds as well. Our services run on a variety of underlying compute infrastructure. AWS has EC2, EKS, GCP has App Engine, GKE, GCE. For each of these services, the cloud provides APIs to control the IAM level access. They allow you to do some org level policies, but the way we've designed our infrastructure is we segregate for IAM segregation instead of network segregation. So we actually end up with a lot of disjoint networks, a lot of VPCs across a lot of projects, a lot of accounts in AWS. We have to deal with transiting across the internet for access between these networks in each cloud. The clouds are generally open by default. We have this issue where the GCP, AWS, they want you to get your app up and running as fast as possible. If you have a POC, they want you to get it up and running in under 10 minutes, apparently. We have the primary issue we have is App Engine is open by default. It's routable on the internet. That's for both ingress and egress, goes out over the internet. And there is, at least now, there's an ability to firewall it, but it's not there by default. So we've had to create tools to add that gating after the fact. So the constraints we're dealing with, like I said, networking. We've got a lot of disjoint networks. We don't have one single connected network that everything is internal, not exposed to the internet. We've got limited enforcement options provided by AWS, GCP, especially at the org level. They allow us to create a shared network, but they don't allow us to enforce everything that goes on that network. So we have to build the tools to do that. And then also some services like App Engine, they don't even work with those internal networks that they're providing. And then on the CI/CD side of it, we actually put our gates in front of that. So before the developers even write any code, we've already gated their project as soon as they create it. We're not in the deployment pipeline. We're much sooner in the process.
Yeah, so to make this even more complicated, it makes it really unclear in the cloud when security should get involved with an app. And if we look at the standard development lifecycle of an app, you start out, you put your app up, you create a new project, and it's on the internet. And you start building on the internet, and maybe over time, you'll come to security because you want a DNS record or a certificate or something like that, and we'll do a security review. And then more time goes on. Once you've done the security review and fixed things, you're now getting feedback on your app, and you're making changes. And throughout this entire process, your app has just been living on the internet. And so you have this sort of pre-launch and post-launch world, and in both cases, you're exposed to attacks. And we really only have guarantees from security in this one little slice in time. And so we looked at this and we said, this is not working for us. This doesn't allow the security team to effectively provide any guarantees. And we wanted to stretch that red line basically across the entire spectrum. So we looked at a few approaches for doing this. One of the things we talked about was we worked with finance to control billing for apps. And we said no one gets billing until they've done a security review. And this worked for a little bit, but there's a ton of features the cloud offers you that you can only have once you have billing set up on your app. Additionally, a lot of teams wanted to test different architectures at scale, which they can't do without billing. So we ended up creating all these exceptions where we were saying, we'll give you billing, but you have to come back and do a security review later on. And it just became a bit of a nightmare to handle. And it was more exceptions than it was just normal approval cases. So the next thing we did is we created some libraries, and we asked developers, hey, please implement these auth libraries in your services. But we noticed people either misimplemented them or implemented something else altogether. And so we were constantly running around trying to validate, have people implemented the correct thing. And this did not scale for our team at all. It was just a really heavy ops load. So another thing which we considered for a bit was just using firewalls to gate things to the corporate network. Problem with that is it really isn't very granular. So any employee can now access any single service. And for service-to-service communication, this doesn't work at all. Like, again, going back to App Engine, every App Engine project egresses from the same IP range. So you can't make any guarantees about what's yours or what's someone else based on an IP address. So the last thing we looked at was Google's identity aware proxy, which is this OAuth proxy you can stand up in front of your apps. And they've got APIs to turn it on and off. But before you can turn it on, you have to have an OAuth client. And an OAuth client, there's no APIs for creating that, so you have to create that all manually. And because of that, it just was not going to work for the vast number of services we have, and because it wasn't automatable. So we looked at all these problems and we said, okay, we've got 4 goals in mind here. The first goal is we want whatever our solution is to be very flexible. We've got a really wide array of technology used at Snap, and we wanted to, rather than force everyone to standardize on technology, decouple those problems and try to make our solution have very minimal opinions about how developers build their services. For high QPS things, we noticed as we were building the solution out that we did have to make a few more constraints, but we did try to keep that to a minimum. The next thing is we wanted developers to not have to instrument their services at all. Every time we had to go audit them, it doesn't scale and it's a heavy ops load. And we also wanted this to be very granular. We want to be able to say this set of users can access these services and these 2 services can talk to each other. And the entire thing should be automated. We shouldn't have to be manually setting things up throughout this entire process.
Yeah, so the way we built our solution is we need 2 basic features. We need to be able to control the network, and we also need to have visibility into the inventory of our cloud infrastructure. So our solution combines quite a few of the things we talked about before. We have a central service that enables billing. Billing's enabled right away, but it gives the security team network management access and visibility into the infrastructure to ensure that the network stays the way we need it to stay to provide that gate. So going back to the development lifecycle, we were in this world of pre-launch and a post-launch, and with an optional or a encouraged security review in the middle. At some point in time, to this world of unmanaged and managed services, where to get into this managed world of production level services, you have to file a security review, especially if you're opening something up to the world. So we're going to go over both of these separately. The unmanaged is lower scale. The managed is much higher scale. So for unmanaged services, there's 2 types of services here. New services in development, POCs, experiments, things we don't know if it's worth the time to even do a security review, if it's never going to see a public endpoint, and internal tools. Those are low scale, employee only access. We treat these identically from the security team standpoint. The scale is appropriate, and they both need authentication, authorization controls in front of them. So to do this unmanaged services gating, we have 2 components. A firewall manager that's managing all the network components, and the stateless auth-n, auth-z proxy that's providing the authentication in front of everything. The firewall manager, we basically, we have to import everything from the inventory. The inventory is pinging the firewall manager, letting it know when it needs to go gate something new. That is all automated, so it happens very, very fast after creating a new project. Then we have a set of base level firewall rules that we've deemed safe. That's allowing traffic from our stateless proxy, especially for App Engine. And then we have an SSH proxy that does the same thing on that protocol. And a few other internal only firewall rules that we allow. And then it constantly is monitoring the state of the VPCs to ensure that developers aren't changing those, and we revert any non-approved rules. So the architecture looks like this. The service inventory pings the firewall manager. Firewall manager is also storing a source of truth. It is basically the exact same data that's in the fleet, but we have to store what we believe is the source of truth so that when we scan the fleet, it's synchronizing and making sure that the firewalls are correct. If a developer changes one of those, accidentally opens something up, even purposely opens something up, we're going to change that back, and they have to come back to us, and we'll be able to update the rules through our firewall manager instead of the cloud directly.
Yeah, so rather than using firewall rules to just gate to IPs, we're just using firewall rules to close the service entirely down. And once we've done that, we now need to open up channels again for either employees to start accessing services or for services to start accessing each other. And so that's where the stateless authn and authz proxy comes in. So it should handle exactly those two cases. It should be incredibly easy to set up. So in the case of App Engine, this is just set up by default for our developers. For other services, there's a small config change they have to make in our proxy, so that way we know how to route to them. And it should stay in line with our ACL service, so we know exactly the right ACLs, and we can enforce those. And the really critical thing is this has to be reliable. And the reason for that is just because this sits in front of all of our internal infrastructure. So if this goes down, developer productivity drops close to zero. So there's three main components to this proxy. The first bit is managing configuration. That's both ACL configurations and routing configurations. And then actually doing the authn and authz. And finally, actually proxying these requests. So for the configuration, there's two types. Like I said, the first is routing. And so we just have a config file checked into source code. Developers can go make changes to that. And we can then go approve those changes to make sure it looks like they're not trying to route to something outside of our network or outside of our org. And then as soon as those are approved, we upload that to GCS. Similarly, we've got the service which we've called a rotator, and it pings out to our ACL service to fetch all the ACLs for our fleet. And then it takes those, transforms them, and pushes those up to GCS as well. Our proxy then actually reaches out to GCS every 10 minutes and gathers all that data, loads it into memory, and then uses that to route requests appropriately and do authn and authz checks appropriately. And what's really key about this infrastructure is that if any of these services go down, if GCS or the ACL service goes down, it doesn't take our proxy down. We can keep running on stale data, which allows things to stay available. And because all these changes are happening out of band, we don't have any inline dependencies. So it increases reliability and reduces latency. There we go. So for the actual proxying, if a user is to proxy into the service, how it works is they in their browser will go try to talk to the service behind the proxy. If they're not authenticated, the proxy will redirect them to Google's IAP, which is their OAuth proxy, which sits in front of this other service we've called the jump point. IAP, they'll go through an OAuth dance with IAP, and Google will then forward us their identity to the jump point. We'll wrap that and return it and redirect the user back over to the proxy. The proxy can now unwrap that identity, set a session for that user based on looking at its ACLs if it chooses to authorize the user, and then forwards the user's request onto the actual proxy. And now the user can just communicate through the proxy. There's two things which are important to call out here. One is for this OAuth dance that we're doing. One of the original ideas we had was to do OAuth in the proxy itself rather than out at this jump point. There's two problems with that. One is it makes the proxy not stateless, and we want the proxy to remain stateless. The second one is that it allows the proxy to impersonate any user that for a service, any user that tries to talk to that particular service, that service would now be able to authorize or to authenticate as that user to any other service. And I'll walk through that attack in a minute. But the other cool generalization here is that this IAP jump point is really just a single sign-on provider. And so you could have any single sign-on provider here, as long as that returns a token that the proxy can unwrap, that would work. So to actually go through this attack and the reason why we didn't do the OAuth at the proxy itself. So because we can't automate the creation of these OAuth clients, and we can't automate the creation of client IDs and client secrets, the idea we had originally was to throw a fixed client ID at the proxy. And you'll see how this breaks down. So the user authenticates through the proxy to a malicious service. The service now opens a new window. It sends some JavaScript back, opens up a new window, kicking off an OAuth flow. So the user goes to the OAuth provider, in this case Google, and gets, if they approve the OAuth grant, they'll get redirected back to the malicious service, or to the proxy rather, with an authorization code. But because our malicious service is running on the same domain as, as the proxy, because it's being proxied, it can now read that authorization code out of the request, even though the proxy hasn't forwarded it along, just by taking advantage of the same origin policy. Now that it has the authorization code, what it can do is it's going to enter this race condition where it's trying to authenticate on behalf of the user to this benign service faster than the proxy can authenticate to the OAuth provider. So what's actually happening here is anytime our services are talking to each other, they're going to go through this proxy. So it's going to hit the proxy. The proxy is going to say, you're not authenticated, you have to go to Google. It'll send them a redirect over to Google. Rather than going to Google, because they have the authorization code for this user who is accessing their site, they can now send this authorization code back to the proxy. And at this point, the proxy will take that authorization code and send it to Google. So you now have two instances of this proxy competing against each other for who gets to Google first. And if the second proxy wins, if the proxy in front of the benign service wins this race, the proxy will end up authenticating the malicious service to the benign service as this user. And so now the malicious service is able to take any of its identities that come to it and replay those against other services. So that's why we created this whole jump point, to avoid this entire attack scenario. So going back to the actual proxying, how this works for App Engine, because App Engine doesn't have any sort of notion of an internal network, what we did is we said for the static IP addresses of our proxy, we'll allow requests from that into App Engine services, and we'll punch a hole in the firewall specifically for those IP addresses. For non-App Engine things, we have this leaf proxy where we VPC peer it to any service that our developers create, and we can now route through that. And so the central proxy can do the auth and an auth-z, and then we route out through these leaf proxies. So this works for low scale things. There's basically two big problems here. One is latency, because we've added an additional hop, particularly for App Engine. And the second one is cloud's bill on egress, or at least Google and Amazon. And because of that, because we're egressing twice, we're getting billed twice for all of our traffic. And so this becomes incredibly expensive if we want to do high QPS. So because of that, we then created this world of managed services, where users don't have, or developers don't have to move to managed services unless they're trying to have high QPS or user data. And we've created, a different sort of suite of tools to handle this case.
So the goals here are to avoid some of those problems. We need very low latency. We need this environment to basically be transparent. We also need it to be cheap. We don't want to be adding any overhead on cost. We still need granular authentication, authorization, and we want visibility into what's going on in this production network. So the components here to build this out, we have an API gateway. That's our front proxy. We have a service mesh. That's where all the services live and communicate with each other. We have a central configuration controller that's managing how everything is routed, authenticated, et cetera. And it's the command and control center for users or developers to configure things. And we have a service sidecar that allows the service mesh to work appropriately. Most of this is working with the help of Envoy. Envoy is a proxy first created by Lyft and now is an open source proxy. So the first component here, API gateway, This is Envoy configured as a front proxy. This is the central entry point. It's got authentication filters. These are managed by the security team. Some of them written by the security team. It's it's one point that we have to look at and audit and understand for the ingress traffic to our environment. And it's centrally managed via the Envoy XDS protocol, which we'll get into. So the service mesh, this is what sits behind the API gateway. The API gateway understands how to route to each service that lives on the service mesh. It's all configured via the configuration controller. Envoy here is also providing authentication, encryption, metrics, and none of this is routable from the internet. So we don't have the problem where we have in some of the other environments or services that we deal with. So the central configuration controller, this is like the brain of the system. It works by the Envoy XDS protocol. It's basically how Envoy communicates to central service and downloads its configuration state, routes, authentication, filters. So because the routes come with authentication and authorization built in, we have an approval workflow. So anytime that service A needs to talk to service B, the owners of service B have to approve that service A is allowed to talk to service B. And then that builds in the authentication authorization. The services don't need to use a library or anything like that. So the service sidecar, this is what enables that to work without building anything into the application. So Envoy is running as a sidecar. We also have a component that bootstraps the identity. Because we want this to work in multiple clouds, each cloud has various primitives that allow us to establish identity of either a VM host or a role or a service count. So we basically take whatever that is in whichever environment we're in, connect to our central CA to pivot from a cloud native identity to our internal mesh identity, which is understandable across every cloud, every service that we have. So then once it gets that identity, it's able to take that identity and go to the configuration controller, which knows which configuration to send to that service, which is how that service then authenticates traffic. It knows how to set up the routes, does all the service discovery there. And then it also exposes a port locally for the egress traffic of the service to be routed externally. So this means the services or the application developers don't need to do any like TLS, encryption. They don't need to do authentication. They're just sending raw traffic, either HTTP, gRPC, and Envoy is adding those components on top. And it also gives us visibility with all those metrics. So some of the challenges here, we've got a little bit different onboarding experience than the first environment we talked about. It's not quite as automatic. When a service owner wants to go into this managed world, they have to basically they have to be able to create their application in a container and go to the configuration controller, set up all the routes. They need to get all the right approvals. So there is some onboarding friction there. And then there's this noisy neighbor problem where we've moved from everybody is in their own account. They deal with cloud quotas for resources, API limits individually with the cloud. Now we live in one VPC, one account, so we have to deal with that at an infrastructure team level within Snapchat, and then we deal with that with the cloud separately. So we have to make sure that one team doesn't use up all the quota for the rest of the company and take out some unrelated service. So that's a new problem or challenge that we have. We also have this, because we've centralized on one ingress point, we do have a potential centralized point of failure. But because it's simpler, it's a single place where we're putting all of our authentication filters instead of every application across our environment. It's not a library that developers have to integrate and get right every time. It's in general, it's it's because of the simplicity, it's easier to manage.
Yeah, so we're trying to get everyone into this new mesh world that we have, but we still have this problem of we have a bunch of existing services that were created and they aren't built for the mesh right now, and they existed before we had a lot of these controls in place. So in order to handle this case, we first did a lot of introspection to think how we're going to solve this problem, and we created something we call the introspection library. And what this is a simple library. It's a line of code to integrate this into any service, and it gets a lot of information about the service that we care about. So it's gathering the routes, the auth controls, it gets all the package info, and a few other pieces of metadata, and we want it to run just on instant startup, so that way it's not consuming resources throughout the lifetime of the instance, and it's pretty predictable, the footprint that it will have on people's services. And because of the information that it's gathering, we can really trigger some high signal alerts that we can operate on, so that way while services are figuring out their migration strategy over to the mesh, we can have a lot of confidence in their current posture. So the way this all works is, again, we've got that central billing service which just enables billing for every new thing we create, and that just pings us that some new service has been created. So we can then go to GCS or S3, and we can set up permissions and roles for that service to write to our buckets. For the service owner, they'll then incorporate this library into their service, and they'll, as soon as an instance starts up there, they ping our buckets, and we periodically go to these buckets, we aggregate the data, we analyze it, and then we can trigger any alerts based on different things that people have done. Like they might not be using our auth libraries anymore, or they might have opened up an endpoint with no auth whatsoever. And the reason we have this architecture rather than service A trying to reach back out to our introspection backend is kind of twofold. One, it's a little bit easier to use just sort of cloud native authentication mechanisms with roles and permissions. And the second one is because we wanted to keep this library very simple and not have to manage state and understand one version of a service might have 50 instances, and instead write on every single instance. We have this thundering herd problem where if we get a spike in traffic, we might have thousands of instances suddenly spin up, and so we want them to write to something that's very highly available, so that way we can guarantee we're still getting the data we want. Yeah.
So going back over each of the components that we've got, we're able to gate our network traffic with the firewall manager. This effectively creates a perimeter around our infrastructure, even when there isn't one there by the cloud itself. Then we create the proxy. The proxy is what's providing that authentication and allowing that trusted path into our infrastructure. We have the API gateway and service mesh because that didn't scale to our production level traffic, but we still wanted all those same security guarantees. And we have an introspection library to understand the internals of our applications. That allows us to understand the changing state over time and know when we want to go look at an app. If something changes that's actually interesting to us, we can actually ping them and trigger a security review instead of waiting for them to come talk to us. So going back over the goals, we've created a system that's flexible. We don't require, especially in the beginning, we don't require any developer teams to abide by any specific language or libraries or rules there. When we get into the production environment, there's some caveats there, but that's only for the production load. Scalability, we've created this system to allow for the developers to just deploy their app and it's immediately available. They don't have to ping us. We don't have an ops team that's setting this up. It's granular. We're getting real identity authentication, authorization instead of IPs or something that doesn't really get you that authentication you need. And it's automatable. We're not there with the ops team and setting things up for everybody. So going back and looking at the way to do this from a clean slate, you're moving into the cloud or you're in the cloud, you start by getting visibility into that infrastructure, laying the foundation. you need to inventory and see what you have. Without that, you don't know where to start. You don't know what you're looking for to put a gate around. Then the first step, start to create a perimeter firewall manager, and you can start with IPs. That's how we started, and that allows you to start to at least stop the bleeding. You know what's coming into your network. Then you can add granularity. The IP-based auth is not granular enough, especially for services that require employees to authenticate. So you can add this stateless proxy. This allows you to really have authentication, authorization controls that allow you to understand and control what's going on in your environment.
Oh, I went too far ahead.
And then as you transition to the production environment, in this world, you're still doing a manual review, but you've solved the first half of our development lifecycle problem. So, and a lot of those things might never get to the point where they need to launch into the production world, so it really reduces the ops load. Then you can start by understanding what's in production. This introspection library, or something that can see what artifacts are being used, especially versions of artifacts, or third-party artifacts. That allows you to see what's changing over time. If a security vulnerability is reported, you're able to target the applications that are in production that need to be updated. And then lastly, you can create a API gateway, a service mesh. This really allows you to provide those controls in production. Instead of seeing what's going on, now you can actually control what's going on.
Yeah, so along the way as we were going through this, there were a few things we learned, which I wanted to go over. So one of the first ones is when we started this whole thing, we were kind of doing this whack-a-mole game of teams coming to us asking to be reviewed, or us trying to find dangerous services and reviewing them. And we realized that did not scale at all. And so instead we doubled down on engineering and really tried to build reliable, scalable services. And through that, we've been able to accomplish much stronger security guarantees than just manually looking at things and reviewing services. The next one was gaining a central hook into the fleet early was incredibly valuable because it began to stop the bleeding of inventorying. We were able to go back, and we now had a finite number of things to go back and inventory, and this allowed us to just see what it is that we have running. And so on a similar note, we think visibility it's much more important to get visibility before beginning to enforce things. One, because it allows you to figure out what's the right type of enforcement you should do. You can start to understand what your fleet looks like. And secondly, it lets you just prioritize what should be gated first. If we think about security very fundamentally, like a security problem is just a developer making an assumption in code and not validating that assumption. And so what we've tried to do with this entire architecture is keep things very simple. Because if things are simple, we can easily understand what the assumptions are that we're making, and then take these very simple just artifacts that we've created and deploy them really broadly. And through that, we're able to guarantee much stronger things about our security posture than putting a black box up in front and sort of hoping it's defending us from attacks. And finally, we've really tried to offer engineering teams a carrot throughout this entire process. So we wanted to build things that are reliable. We wanted to abstract away a lot of the authentication and authorization work, so they don't have to think about that. With things like the introspection library, because it's getting all the routes and the auth controls, it's basically self-documenting a lot of their APIs for them, which engineering teams seem to like. And yeah, by offering them a carrot, we really galvanized support for this entire thing. And yeah, got it to the scale it's at Snap. So with that, we can now sleep better at night. Yeah, we wanted to spend some time doing Q&A, so if you guys have any questions, we'd be happy to answer them. Thank you all. There should be mics somewhere in the middle there.
Okay. So which technology is used in the stateless proxy?
So
In the stateless proxy. We basically wrote a somewhat simple Java proxy, which just runs on Kubernetes.
there are some open source versions that would do. Envoy itself could potentially be used, and then there's a Bitly OAuth proxy that we had used in the past, but we don't use that one anymore.
Yeah.
Hey.
I can't see, so you're going to have to just talk.
So yeah, we kind of went through a different scenario. Basically, our infrastructure guys built services that that projects can plug into, and so they restricted what networks, for instance, each project would be able to plug into, and then provided the underlying network services to those projects. Is that something you guys thought about as well?
Yeah, so looking at GCP, that sounds much more like their shared networking model. And at least when we started, that wasn't available yet. And now that it is available, it is what we're doing in our production world. One of the problems we see there is that things like that might be available in one cloud but not another. So we've typically gone with whatever the lowest common denominator across the clouds, in our case AWS, GCP. So even if something's available in one of the clouds, we might not use it just because we also want the same thing in another cloud that doesn't also provide that. I think AWS is coming out with a shared VPC model, or they have one. That once that's available and tested, we could consolidate everything and use that. But we also have to enforce that things like App Engine aren't used because those aren't part of this shared network model. And we have a lot of things on App Engine, a lot of developer experience on App Engine, so I don't think we're ever getting away from that world.
Okay. And then I was interested in your enumeration project. Like, how do you figure out everything that's running in your service? Is that running in a project by itself then? Separate one?
Yeah, so the way, that one actually has to be different per cloud just because it's dealing directly with the APIs in the cloud.
Right.
So in AWS, I believe they provide you like a JSON dump. I forget the name of it, but they just give you a JSON dump of everything that's deployed in your org. And in GCP, we've created a project or an application that can scan everything we care about, and that has hooks to ping things like our firewall manager to provide or to gate that back down if anything happens.
Yeah. Once we created that billing service as well, which just enables billing, that really became a choke point for us to identify, at least at a project level, everything that exists, because it just forced all the developers to come to us and say, this is my service, please turn billing on for me.
Yeah. In GCP, also the IAM works at an org level, so you can give access across everything, where in AWS, it doesn't quite work that way. You have to assume roles into all the other accounts. So it's a little more difficult in AWS to make that work with a central service.
Okay, thanks.
Yeah.
Where do you see the next evolution of your security model? Maybe building in some auditing capability to make sure you're compliant?
Sure. So, yeah, we do have. Sorry, this is kind of focused on. You're over there, maybe. Yeah. Yeah. So what we've built is very focused on authentication and authorization, or what we've presented rather is very focused on that. There's a lot of other components we've built around these services to do things like auditing. Okay. One potential thing we've talked about is more establishing a sense of user presence, meaning if one service wants to talk to another service on behalf of a user, we can validate that this really is the user they're supposed to be talking about, and they can't impersonate a user along the way. Those are some of the things we're exploring there.
Yeah, the other side of the auditing side of things, like SOX compliance, comes in on the IAM management side, our central tool that does that, which we really didn't get much into in this talk. That's like what's providing the ACL That ACL service we talked about, so that's providing all the ACLs for everything that the proxy is managing access to. But that's kind of separate from what we discussed, I guess.
And real quickly, how long did it take you to build this, and how many people?
Yeah, that's a good question. We started out on this probably close to 3 years ago.
Yeah.
Yeah.
And it's come and go. Like some teams have come and gone depending to help out, depending on what component they may need. Especially now with the service mesh, that's become a much larger component than even just security. That's our internal infrastructure team is working on that. So yeah, it's a lot of people and it's been a lot of time, but we've done it gradually to kind of stop the bleeding and make sure we're not spending all of our time on the ops load and manual reviews in the process.
Yeah, and then in terms of the number of people we've allocated to this, so the firewall manager, I think that was just the 2 of us.
Yeah.
I don't think anyone else worked on that. The stateless auth proxy was about 6 people for the course of a year or so. And then, granted, throughout this process, we didn't start with the designs that we have right now. We started with very different designs, and so that elongates this process quite a bit. And we tried out a lot of other things. As I kind of talked about at the beginning, the introspection library is about a year or so. The hardest part is just integrating this with all these services, because it does require developers to add this in. So we've tried to reduce that complexity quite a bit, and also architect the thing appropriately. We again went through a bunch of different architectures for that, but that's 3 to 4 engineers working on that one. And then the service mesh is the really big piece.
Yeah, so the service mesh, doing things outside of the in-process or in-app libraries really speeds up our development time. We only have to write authentication for one code base instead of providing a library to the entire org that writes in 4 or 5 languages at scale. So that's allowed us to focus on fewer things and do more.
Yeah.
Great. Thank you.
Yeah.
Hi. So you guys built your firewall manager by yourself?
Yeah.
You didn't use any other vendor to do that?
Yeah, so it's basically it's just an App Engine app. It's scanning our firewall state across our infrastructure, and it has its known state internally. And because they're providing all these APIs, it's relatively simple to just scan those APIs and then reset anything that isn't in the appropriate state.
And it differentiates in each project?
What's that?
Probably you have a lot of projects in GCP, so it tell which project and what's open and what's not?
Yeah, so the access model we have is like owners of projects, and at least in GCP, this is so anybody that needs to create an isolated set of resources would create a new project. They would then become the resource owner for that project, and our firewall management tool is able to see that. So yeah, we have on the order of hundreds of projects.
Thanks.
Any other questions?
Cool.
Cool.
We'll be available for...
Yeah, we're happy to hang around and chat if people want to. Thank you so much for coming. Thanks.